All right, so in this video lesson, we are going to study about the divergence and the curl of a vector field. So, studying about these the operations on a vector field right here, I highly recommend, before we get into the video lesson, I highly recommend that whatever we learn right now, keep that as an operation that we can do to a vector field right here. And then as far as seeing some real applications of that, it may have to take you into some other applied courses, such as physics or fluid dynamics or something like that. But we probably won't see as much direct applications right here in this video lessons, other than just purely studying about these as an operation that can be done on a vector field, like that. So that's one high recommendation of mine before we get started. Okay, so other than that, let's get in and find out and study about what they are, the divergence and the curl of a vector field. Okay. All right, so to know what a divergence is, let's start out with learning about a divergence. But for a divergence or a curl, we are going to start out with a vector field f of x, y, z, being a vector field with p with components p, x, p, q, r. All right. So let's start with just a vector field in R3 right here. So capital F being a vector field in R3. Okay, meaning each of these components here is a function of three variables, is a scalar function of three variables, and then this is here is a vector field. So now it comes to the definition of what a divergence is. Okay, so a divergence of a vector field, as some worded definition, the divergence of the vector field F, denoted by this notation right here, simply defined by the partial derivative of p in respect to x plus the partial derivative of q, the second component, but in respect to y, plus the partial derivative of r, the third component, in respect to z. And so that's why, as I said earlier in the beginning of our video lesson, we are simply going to see this divergence of the vector field simply as an operation. So what we did here is that we calculated right out of the three components here, we calculated the partial derivative in respect to x for the first component. We calculated the partial derivative of the second component in respect to y. And we calculate the partial derivative of the third component in respect to z and add the three scalar partial derivatives together. And that's how we define the divergence of the vector field. And then as far as what it's for, what it's good for, you will be able to explore that in the other courses outside of this particular course right here. Okay. And so in that way of how we understood that, then let's take a couple of remarks right here. And actually this is, for now, at this point, this is the only remark, but if we're looking at the way how the divergence of a vector field is defined right here, then this is any of these is a scalar function. So each one of the components of our vector field is a scalar function, and then taking the partial derivatives will once again give scalar functions. So in the end, the divergence of a vector field is a scalar function. And so that is one remark for now. The divergence of F, and that's the symbol right there. The divergence of our current vector field is a scalar function of x, y, and z, and of course three variables. Okay. And so in that way, let's look at one example right now. Right, so this example number one is specifically intended for getting us comfortable with calculating the divergence of a vector field. All right, so right now we have an example, and in this example we are given a vector field in R3 right here, and this is the P component, the first component of our vector field. This is the second component of our vector field, and this is the third component of our vector field. And so each one of these components, as I said earlier, these are all each one of these is a scalar function of 3 variables. And now let's calculate the divergence of this vector field right here. And so the formula is still being retained on the other board of mine. Right? So calculating the divergence, all we need is the partial derivative of the first component in respect to x, the partial derivative of the second component in respect to y, the second variable. So it has that certain order, so easy to keep track of. And then the partial derivative of the third component in respect to the third variable, dz. Okay? And so in that way, we can easily, so there are many styles of approaching it. I tend to write down the 3 separate partial derivatives first. So dp, dx, this is p right here. Okay, so dp dx here has to be z. Okay, dq, dy, this is y. Okay, this is q. The middle component is here. So taking the partial derivative of q in respect to y gives me x, z. Okay, and then dr, dz. This is r, the third component of our vector field. And so we're going to take that the partial derivative of the third component in respect to the third variable. And there's no third variable in here in this particular third component, so it becomes just a 0. And so in the end, the divergence of this vector field comes out as easy as just z being dp dx plus xz being dq dy plus a 0. And that is the answer to our divergence of the vector field. Okay, and so now looking at the vector field, looking at this final answer of the divergence, once again it agrees consistently with that remark I've written earlier that it is a scalar function of 3 variables, even though the y variable is absent in this particular one right here, but generally it's a scalar function of 3 variables. Okay. All right, so now let's turn our attention over to what a curl is, the curl of a given vector field. So again, with a vector field f in R3 given with 3 components, p, q, and r right here. Let's find out what the curl is. Okay, so let's study about the curl. So let's have a briefly worded definition. The curl of this vector field f here is defined by, okay, and so now this is what I have. Notationally, curl of f, and it's defined by dr dy minus dq dz with the I vector plus dp dz minus dr dx. These are all partial derivatives with the j vector plus, and the last one here, dq dx minus dp dy with the k vector. And so this is how we define the curl of a given vector. And so before we get started into any of the examples right here about calculating the curl right here, observation right into this definition, it's the way of how we calculate, so it's the way that defines an operation. And this operation is called taking the curl of the vector field. But then looking right into this operation, it looks like the final answer here, let's look at all these I, J, and K components being involved right here. So it rings a bell immediately that as a remark right here, then the curl of F, okay, or the curl for any vector field is a, see, this is a function of F, Y, and Z. I mean, this is a function of three variables X, Y, and Z. This is a function of X, Y, and Z, and this is also a scalar function. But now together with three scalar functions with the I, J, and K components right here, then the curl itself is a vector field. So not necessarily the same, and it shouldn't be the same, but a vector field, it's another vector field. Okay. Okay, so the curl of F is a vector field. Okay, so that's one important thing right here, and more precisely, a vector field in or three, with three components. Okay, so keep in mind the curl of any vector field is another vector field itself. Being the same with the original vector field, that's a different story to consider. All right, and so from now on, I mean at this point right here, right from this point, we are ready for looking at one problem that's we can learn to calculate the curl of a given vector field. All right, so before I call an example, let me bring up a problem so any one of us can think about a situation and we can start overcoming that situation and to derive something even better, and then we're going to use that into a formal example. So let's call this now a problem, just simply a problem. That what about when we are given simply a vector field of three variables, right, in 3D in R3 space, being xz, xyz, and minus y squared here. Now with this vector field right here, what if we are asked to find the curl of F? What if we find the curl of F? So this problem itself could be brought in as an example, but think about it this way right here. The only tool we know so far is to go through the formula, which is right now at this point, this only formula that I have given out is quite challenging to remember and to operate in. As a matter of fact, if I would do it, I'm still going to need to swing back and forth to look at the formula to apply my curl calculation correctly, because it involves all of the crazy and hard to keep track of dr, dy, and then the dq, dz, and then do a subtraction, and then the dp, dz, and dr, dx, and then do a subtraction and put that together, associate that with the j component, and then there's a dq, dx, and dp, dy, so all over right there. Okay, and it's hard to keep track which difference goes with the I, which difference goes with the j, and so basically we have to, or either switching back and forth between the two boards here when I'm working in front of the camera here, or I have to always constantly hold on to a paper. And so doing it this way with the direct formula is not productive at all. And so eventually we will have to face that problem that we work through a vector field to find the curl right here. But so I have pointed that out. Memorizing that formula is really a challenging work. It's not that simple. And so now let me put this aside for now. Okay, let me put this aside for now. Okay, anyone can really pause the video and try independently to apply that formula I've had right there to calculate the curl of F independently. Okay, but for now I brought up the problem just to point out. That it's currently extremely challenging, right, to calculate the curl for any given vector, simply relying just on the formula through that given definition. And so in this way right here, allow me to point out another nature. Okay. All right, so that nature of the curl that nature of the curl that I was about to say, here's how it comes. Now, this lesson is supposed to be learned after you have already learned about what a gradient field is. Okay, it's the way how it is for learning in vector calculus. And so at this point, anyone viewing this lesson must be fluent with this symbol right here. So if we have a scalar function f, then this symbol right here, the delta, but the upside down delta, so the del f right here is the gradient vector of f. And so what it is as a reminder, as a brief reminder, then from where the scalar function is, we're going to take the partial derivative in respect to x. Okay, I purposely write that kind of little bit spaced out to indicate that partial derivative itself is an operator being operated on this function f. Okay, and then we take the operator on the same function, but we operate that with the operator dy right here, meaning we take the derivative of this function in respect to y, and I purposely wrote that a little spaced out right there, so we can see that the dy right here is an operator. See, there's the dy, right, operating that function, or being operated on that function. There's the dx being operated on that function. And so similarly, the gradient vector has a third component being dz right there. Okay, so df dz, and so once again, the way how I see it, there's an operator dz indicating that we're taking the partial derivative of any objective function. Okay, when we attach that to the left side of any function, that says we are calculating the partial derivative in respect to z. So this symbol itself is not an expression. That symbol is not an expression. It's an operator. Okay, it's indicating what to do with a function. All right, and so in general, now the way how I see it, so in the end, we can kind of draw out just the del symbol. So del f itself is a vector field. The gradient of f is a vector field, and it's a vector nature right here. And so we can kind of draw out that, hey, let's draw from that experience, we're going to define the del operator. So this is an operator, but being in a vector nature. That the del notation here, the del operator as a vector, okay, contains three components. The operator d dx, comma, the operator d dy, and comma, the operator d dz. Okay, and so think about it just like that. When we apply this to the left in the way how we write notationally, if we apply this operator from the left of the function, that means we go df, 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 dy, df dx, df dy, and df dz, and that's how we have the del f here producing the gradient for us. Okay, and so now at this point, I have just introduced for anyone viewing this lesson the del operator, the del f operator. We can just simply call it like that. The del, short for delta, the del operator. Okay. But what's good about defining this del operator separately? All right. So now let's look at the following. Let's say we have a vector field of three variables with three components, p, q, and r. A vector field of three variables, three variables and then three components. So a vector field in all three. Okay, and so now let's do this again. Even though it's not really a vector, but I have already said the del operator is taking that vector nature, is having that vector nature, that vector characteristic. And so seeing the del operator as a vector, we can do the following. I'm going to go del cross f. Okay, let's try it. Let's experience it. F clearly is a vector, but note how I apply that operator through the cross product from the left-hand side. Okay, so del cross f from the left-hand side, and according to the way how we already know how to do cross product, we set up the ijk component. Okay, in a determinant, and then the first vector here being, even though being only an operator vector right here, the del operator vector, but we can just go ahead and write those in, d dx, d dy, and d dz. That's for the first vector. And then the other vector comes, of course, the p, the q, and the r. Okay, and so now once we're writing it like this right here, then just think of that as in the usual way. If this really was a vector, how do we take the cross product of these two vectors right here? And so, in the way how we work with the cross product, anyone viewing this lesson has been fluent enough with that. So now I'm going to think of, it's not really multiplication. What we think about, we attach these together in a multiplicative way right here. So now I have dr d dy, and then minus the other cross diagonal entry. So minus dq dz. Okay, and that comes with the I component. So the I component comes out from expanding out this 2 by 2 subdeterminants. Okay, and so note, I'm going to swing back to the formula. Note how that what I have just found looks exactly like this that we've had so far. All right, and so that's starting to tell anyone viewing the lesson a way to go from here. And so in that way, let's continue. So for the next one here, we're moving over to the j component, but with a minus sign. And so now here we have the j components. Okay, with the j components here, we're going to need to go with these 4 entries. So it's going to be a d r dx minus d p dz. Okay. All right, and so it's looking almost the same with this middle component, except for here it was a plus sign and these 2 terms are in the reversed order. And so the last term here is, of course, so with the k from here, then the subdeterminants we have is right here with these 4 entries. So now I'm looking at dq dx minus dp dy. All right, with the k component. And so needless to say, now with the minus going in, with the minus accounts with that in the middle component, we can turn it into a plus. But now these will become the following. All right, so after we adjust that minus right there, that difference in here flips in the order right there, flips the order, and then that becomes a plus. So now all of a sudden we found out, hey, wait a minute, del cross f, if we're treating del operator as a vector that has vector nature and all that, and taking the cross product between the del operator and the f right here, and our vector f with the 3 components p, q, r, it turns out to be exactly the curl. So this is the curl. And so from this point on, a lot of times in and many textbook authors, and you can see this presented all over different textbooks out there. But yes, upon this definition of the del operator, so curl of f, taking the curl of f is simply understood as taking the cross product between the del, but remember the del is on the left, okay? Taking the cross product of the del operator and the vector field. That's how we can understand that. And then with this way of seeing how we can calculate the curl right there, it's a lot easier to keep track of these I, j, and k components on our curl of the vector field f right there. All right. And so now at this point, upon getting this, quick formula right here, quick understanding to easily remember. It also helps big time memorizing how we can get the curl of a vector field right there. Now let's go back and let's really bring that into an example 2. All right, so here we are at example 2 to continue from the earlier example, and this example here is intended for to calculate the curl of a given vector. All right. So this is our example 2 now, but now you can realize this example 2 really is just a real time that I'm starting to find the curl of this function, of this vector field, even though I have brought it up in that improvised problem earlier. Okay, but for that problem, at that point, I did not introduce the curl symbol and the way how to calculate the curl, the way how to write the curl like that. And so, I left that for a viewer to do that independently with the formula, but now we have a better way of handling it. So the curl for f with the del operator, okay? So the curl of f, okay, is simply the del operator cross with f. Yeah. So del cross f, and setting up the ijk determinant. So now we're looking at d dx, right? D dy and d dz like that. Okay, so that's for the curl vector. And then the other three components, now let's really write them in. So I have xz here. Okay, I have xyz for the second column, and I have minus y squared for the third column. All right, so now let's handle it one by one. So now working this out right here, working out with this determinants, then see, isolating out the I components, and then we have these four right here. So partial derivative of this over in respect to y gives me minus 2y. Okay, minus 2y, and then we're subtracting the partial derivative of this right here, right, in respect to z. So we have minus x y. All right, so that now gives me the I component. All right, and then we need to subtract. Okay, and then now in parentheses. So now hiding out that row, that column and this row right here. So these are the four components, the four entries that we need to look at. So partial derivative of this third component, right, in respect to x. So that gives me a 0. Partial derivative in respect to z of that one right there. Okay, that gives me simply a minus x. Okay, and that goes with the j components. And then now last one right here, plus. Okay, and now it becomes so for the k component, we're looking at these four entries right here. Okay, so taking the partial derivative of this middle column bottom at the bottom right here in respect to x, it gives me yz and minus. Now the partial derivative of that in respect to y is a 0 out with the k component. All right, so theoretically speaking, at this point we're done with calculating the curl. Let's just rewrite it. So now, in the way how I'm seeing it, this here becomes a plus x in the j component. So plus x with the j components. And then this there's no need to write the minus 0, so I will rewrite it. All right, and that's how we're done with our curl. So this is the curl of f right here. All right. But now the invention, I have to call it the invention or the realization that the del can be regarded as the del operator vector, being the d dx with the operator d dy and with the operator d dz. Realizing this, or formulating this vector nature, but only an operator formulating this vector nature thing right here is a fabulous discovery. Okay, it's a fabulous thing that the people realized, that the people formulated, because here's it's going to bring tremendous impact, tremendous consequences. So let's look at a few consequences right here. So now I'm talking about the consequences of using this del right here. So curl you already know, right? Curl you already know is simply found by taking the crossbar products between del and the vector field. So that's no need to talk about. So that one's easy. What about the divergence? Let's look back. I thought we're done with divergence, but let's look back and investigate that one more time. Divergence, okay, of a vector field is in the way. Now that's easy enough, so we can still remember that easily. Partial derivative in respect to x, right, of the p component. I purposely wrote it out like that. Okay, kind of separate it out like that. Plus, and then that is a scalar function, plus the partial derivative in respect to y as an operator apply on the q components, plus the partial derivative in respect to z as an operator that applies on the r components, the third component. So let's have a look. Of course, it's none of these is a multiplication, but we can treat it like the way how multiplication runs. It looks like partial derivative multiplied to the left from the left with p. This part right here, this partial derivative operator multiplied to the left with q. and this partial derivative multiplied to the left with r right here. So that looks like these are the three components of our del vector, and these are the three components of our vector field f right here. So, and products, even though they're not real products right there. And so it looks like I can see this as the del vector dot f right here. All right, and so yes, ladies and gentlemen, as a matter of fact, from now on, from this point on, you are allowed to understand the divergence of f to be done by taking the dot products between the del operator and f like that. It's just a way to represent, it's just to make it easy to represent, but surprisingly it brings all that good usefulness for us right here. So taking the divergence simply is just the same as treating the del operator as a vector. We take the dot product between that del vector with f, but remember, always from the left to the right. From the left to the right. I got to emphasize that. All right, and so that's how we can that's how we can remember, to make it easy, about how we calculate the divergence of a vector field, of a given vector field. Okay. And let's just not stop there. There are a lot better. There are still many more good usefulness of the del operator right here, because with that convenience, it's not a real vector or anything like that, but we can surprisingly have a lot of places to use that. There are a lot of places that we can effectively use that. So let's even explore further of the consequences. So I'm going to say let f be a scalar function. All right. Then so everybody at this point knows that del f. See, think about if we multiply del, right, with f from the left-hand side, it's the gradient vector. Okay, it's the gradient vector, which is also a vector field. df dx, df dy, and df dz. No doubt about that. Okay, but now let's explore. Okay. We're going to explore some more consequences. So why don't we take the, because being a vector field, we are legally allowed it, right? We are legally allowed it to do this. Find the curl of this gradient vector field. Okay, find the gradient of this, find the curl of this gradient vector field. And so now, seeing that as a vector field, and with that gradient, with that curl symbol right now, with that del symbol being treated as a vector right here, as an operator vector right here, and we can do I, j, k. We take the curl right here, and so now there's a d, dx, d, dy, and the d, dz. Okay, and then in the bottom row right here, there's the real df, dx. df, dy, and df, dz. All right. And so in that case right there, all right, these four components again. Let's look at that. We're looking at d square f, okay, over dy, dz, minus, and then with these right here, okay, we're looking at d square f, all right, dz dy, all right, and with the I component. And then whatever you have in mind, I know you already have some the idea in mind about what this will turn out right there, but hold it right there. Okay, we're going to subtract, and then just like that. Now these two components right here, after hiding out the middle row, the middle column right here, these four the entries right here, and so we're looking at d square f over, okay, dx, dz, and then minus, okay, now we're looking at d square f, okay, over, okay, these four components, so d, dz, dx, yeah. And further, I know that some viewers at this point even realize something further about this middle component. Okay, again, I ask you to hold on to that thought there. Okay, and the last one right here. the last one being, with all that there, we're going to add the last one here is going to go d square f, okay, dx dy minus d square f dy dx, okay, with the k components. All right, so let's put these together, and I apologize for my short space on my board right here, but so now we can see this component here is 0, and 0 as a scalar, 0k, okay. These other ones here, that one is also a 0, and that one here is a 0. So why is that? See, this is second partial derivative. Second partial derivative. This is, think about this as this here is f zx, whereas this here is f xz. Okay, and so we have already had that theorem saying that these are always equal, right? That's why the difference here comes out 0. Okay. And so similar argument. Now you can see that this is f xz, and then this is f zx. Once again, same result right there. They have to be equal according to that theorem we've learned from our beginning multivariable calculus learning right there. So that's why that difference is 0. So now in the end, we come out with the vector following 0, 0, 0, the 0 vector. Right. So what we have found, so now we actually have proven a theorem. We do have a theorem as following. Okay, and allow me to only write on the board here the very brief worded version of the theorem, and then this theorem should be given in any of the textbook that you're using. But most importantly, taking the curl of a gradient vector will give us this vector over here, the 0 vector. And that's what it is. All right, taking the curl of a gradient vector will give you a 0 vector. Okay, so that brings us into some connection between curl, what curl has to do with, because in another language, gradient vector is a conservative vector field right there. Okay, and so in that way, I can see that so from that theorem right here, I can formulate the following understanding. The formula itself was written in a very compact way, just taking the curl, okay? Taking the curl of any gradient vector field will give you a 0 vector. So that's from what the theorem here says. But if we're putting that in some formal statements, just some formal statement, and it doesn't have to be with all the details yet. But as just that statement right here, it means if, okay, if f is conservative, see, this is some vector field f right here. If capital F is conservative, a gradient vector field is a conservative field. If f is conservative, then it leads to, okay, then it leads to the curl of f, right, has to come out being 0. So that's another way to understand about this theorem. It's just another way of understanding a theorem. This theorem here, written it down as a statement, as a worded statement. But now, sadly, we cannot rushly use this right here in the converse way. In the converse way right here to say that, hey, if curl equals 0, we'll come out with the vector field being conservative. Because in another lesson that I've done earlier prior to this video lesson here, I've talked about what it means being a conservative vector field, and it's, you know, we come up with different kinds of tests to test for conservative fields. And so at this point, once we've learned about this theorem, somebody start making that connection, and we can go, hey, wait a minute. So can taking the curl be somehow a way to test, or in somehow be another way to test for whether a vector field can be conservative? But see, that thought right there we're having in mind is bringing up the converse of this theorem. Okay, so the converse is sadly not always true. The converse is sadly not always true. However, we do have a theorem. But that limits it down a little bit. Okay, so now let me swing over to the computer screen. All right, so here we go at our theorem on the computer screen right here. If F is a vector field defined on all of R3, meaning it's a vector field that's defined in the entire space of R3 right there, whose components function have continuous partial derivatives. So these are the requirements. Okay, we need to have the vector field defined on all of vector fields, and the components function have to have continuous partial derivatives. If that's so, and further taking the curl of the vector field, taking the curl of the vector field gives out the vector 0, then with that result, with that and these requirements together, then we can make a statement concluding that the vector field is a conservative vector field. So the idea of this theorem is that it's not always true that, hey, just simply take the cross product, take the curl of the vector field and coming out with 0 means the vector field will be a conservative field, because a field itself, some field may not be defined on all points of R3 right there. So some field failed this. Some other fields don't have continuous partial derivatives. So even if we have this condition right here that the curl of the vector field turns out to be a 0 vector, it's still not going to guarantee that the vector field is a conservative vector field. However, if we meet all three requirements here, the vector field is defined on all points in R3, having continuous partial derivatives on all component functions. And the third one important here, the curl equals 0, F is a vector field. F is a conservative vector field. The good news for any one of us here learning from this video lesson is that a good majority of time throughout our study here for this course at our level here, then a good amount of time we're talking about those vector fields where they are defined throughout all points in R3, and they also have continuous partial derivative. And so that's why you can see that you can apply this theorem quite often as a way to check for the conservative. But outside of this course, when you navigate to a more advanced course, be extremely cautious about the use of this theorem right here, because it's limited to only those vector fields where it's defined everywhere in R3 and having continuous partial derivatives everywhere. Okay. And so now on this board, we can sort of pick up that important thing aside from the important details. Okay. So F is defined, right? And like I said earlier, of course, a lot of time it is in our course that we're studying here. And then the partial derivatives, okay, are continuous, okay? Not just only existing, gotta be existing and continuous. So as long as we got these three requirements, and like I said, a lot of time for this course these are these are always met. Then a lot of times you can see that if the curl of the vector field turns out to be 0, then it leads to the vector field is a conservative. So this can be used effectively, at least within the scope of our course right here, as another test for conservative, whether a vector field being conservative or not. All right, and so let's now look at a third example, our example number 3 here in this video lecture right here, that directly applies this theorem. So all right, so in this example, it's just one problem right here, but we want to show that this given vector field in R3 is a conservative vector field. Okay, and so in order to show that, the most important one is to take the curl, right? To take the curl of F, of this given F, and we'll get to that. But then let's quickly check as well. See, the components in the observation right here, each one of the components here are all just simply polynomials in 3 variables, meaning they are defined everywhere in R3. Okay, there's no such x and y and z values that makes any one of these components fail to be undefined. Fail to be defined like that, or become undefined. Okay, and so we have the first requirement checked, and then these are all just powers of x and power of y and powers of z, so we can find partial derivatives easily, and partial derivatives are further powers of x and y and z, and so these are, what my point now is that the partial derivatives are all continuous here, okay, for all of these three components. So now all we have to worry about is to calculate the curl of f, and once this turns out to be a 0, then that's is enough, and that's sufficient to say that this vector field is a conservative, okay. And so now I'm going to go ahead and fire up the calculating the curl work right here. All right, so the curl is calculated by the del cross f, and we're setting up the ijk. Right. And then there's d, dx, d, dy, and dz. And then there we have y squared, z cubed. We got 2x, y, z cubed, and we got 3xy squared, z squared. All right. And then so in that way right here, proceeding further into that, I'm looking at, so for the I component I'm going to write here, and then the j and the k I'm going to have to write in the line below. So now I'm going to have to find the partial derivative of this in respect to y right here. So now it's going to give me 6x squared y z squared. Okay, and then I'm subtracting, and then the partial derivative in respect to z of that function right here, that gives me 6xy z squared. And I just now realized that I had a typo right here. That square is for that y right there, so it shouldn't be a square here. Okay, so 6xy z squared minus 6xy z squared with the I component. All right, and then so that's already showing a 0 right here. Middle components. Okay, so now I'm going to take the partial derivative of that in respect to z. So now I'm looking at 3y squared z squared, and now I'm subtracting the partial derivative of this, okay, in respect to x. So now I'm looking at just 3y squared z squared. All right, and that's with the j components, and so that middle component is also a 0. Now plus, and then the third one right here with these 4 entries, I'm going to take the partial derivative of that, right, in respect to x right here. So now I'm looking at 2yz cubed, and now I'm going to subtract the partial derivative of this, okay, in respect to y. So now it's going to be 2yz cubed, so with the k component. So this is going to 0, that is going to 0, and that is going to 0. So now it turns out the curl here, okay, so the curl of f does turn out to be the 0 vector, and that is enough to say that our vector field here is a conservative. And I apologize that the board space nature is so short, so I have to write that in that informal way right there. All right, so that's how we're proving this theorem, this vector field being conservative right there. Okay. All right, and let's even now find out even further consequences. Let's look at the further consequences. Okay, so now what about, think about, you got a vector field, and then we take the curl of that, and then, so the curl of a vector field, I have mentioned this in a remark earlier, this must be another vector field, so we can legally calculate the divergence, all right, of that curl vector field right there. Let's find out what's going to happen. Okay, let's find out what's going to happen. And so think about it this way right here. Okay, so the curl of f, right, the curl of f will turn out to be, and I need a lot of space right here, because so in the end, the curl of f is 3 vectors in the following form: dr dy minus dq dz. See, and without the determinant, you can see that I have to use a paper to copy down the formula. dp dz minus dr dx. That's the second component for the curl of f. And dq dx minus dp dy. Okay, so this is the curl of f. And we want to take the dot product from the left-hand side between the del operator vector with this vector right there. So that means performing this, right? It comes to the following. It means we have dr dy minus dq dz. Okay, we have that, but we're going to differentiate that in respect to x. All right, we're going to find the partial derivative of this in respect to x. And then we're going to, so this middle component, dp dz minus dr dx. We're going to take the partial derivative of that in respect to y right there. All right, and then we're going to plus, and then the third component, dq dx minus dp dy, and we're going to take the partial derivative of that in respect to the z component. All right, so let's really apply that. And it's not really distributive law, but it works. It also works like distributive law. We got two terms, so taking the partial derivative means we can do it term by term on each one of these. And so now I'm looking at d square r dx dy minus d square q, okay, dx dz. All right, and then I'm going to have plus d square p dy dz minus d square r over dy dx plus, and then I have d square q over dz dx and minus d square p over dz dy. All right, and so now if we're looking at all these 6 components right here, all right, and now we can see this. They're all canceling. That one here cancel with this. dr square over dx dy is the same as dr square over dy dx. They cancel out. This term right here, d square y and d square q over dx dz, okay, d square q over dx dz, they are essentially equal, and they are opposite term. They cancel. And then the 2 remaining terms, they're also opposite term. They cancel. All right. So shockingly, we found out. So after all of this work right here, we found out. Let's go back to this because I'm short of space. Equal to 0, and this is a scalar 0 right here. So the dot product, I mean the divergence of a curl, will always equal to 0. Okay, always equal to 0. And so in that way, we actually formulate into, and what we have just done here is the proof that leads into the following theorem I'm about to show on the board right here. All right, so now as a theorem, and allow me to write only the briefly worded version of the theorem here, and you can find a detailed worded version in any of the textbooks that you're using. So let F be a vector field with 3 components, P, Q, and R. Right. Then simple result that we have proven now. The divergence of the curl of F, okay, will always equal to 0. And that's the theorem that we have just proven. Okay. And so in that way right here, let's look at one example. And here we can call it example 4. All right. All right, so here we go. That's our example right here. And in this example, we just simply want to find out with this given vector field right here, is this vector field the curl of some other field G? All right. And so the only way to answer yes or no to that, we take the divergence, because if this was the curl of some vector field G, then we know some axis, taking the divergence, right? So taking the divergence. So if F being, remember, we are trying to see if F can be the curl of some G. That's what we want to find out. But if being the curl of some for some vector field G, then taking the divergence on that, right, it's going to have to come out 0, and that's what we are doing for here. And so now for that, with that plan in mind, right there, we're taking the divergence of F. All right, and so it's a good time to make use of that symbol right there. Okay, and so here we're looking at partial derivative in respect to x for the x, y, z, okay, plus the partial derivative of the 0 function in the middle in respect to y, plus partial derivative in respect to z, right, of the third function minus x squared y. Okay, and so with this right here, I have that first term gives me yz. The middle term is a 0. The last term is also a 0. So, but in the end, it comes out the divergence of this vector field is a yz, which is generally not always 0. So I'm doing this other than 0 here means it could be 0, but only for some specific value of values of y and z, but not generally equal to 0. And so this one right here, that clearly proves that the f right here is not the curl of some vector field G right there. Okay. And so after that work, we now have a conclusion. F is not the curl of a vector field. All right, that's how we have proven this problem.